I will describe an experiment on thermal relaxation of a serial light bulb. Any dissipative system will relax to its equilibrium position exponentially with a characteristic time constant tau if the external force is removed. For example, you have door closers. You push the door and leave it, the door will slowly close to its original position in a time tau. The equation satisfied by such a system in its return to equilibrium is dx by dt plus x by tau equal to 0. There are examples from all branches of physics for relaxation. In mechanics, a ball moving in a viscous medium, when you remove the force on the ball, the velocity will relax to 0 according to this equation. You have a hot body that is losing heat to the surroundings. You stop supplying heat to the body, then the temperature of the body will decay slowly according to this equation to the temperature of the surroundings. You apply an electric field to a dielectric medium, then you get dipoles in the medium, you get polarization in the medium. You remove the electric field, the electric polarization will return to 0 value according to this equation when the electric field is removed. You take such a system and apply a sinusoidal force of frequency omega is 2 pi f. Then the system will execute sinusoidal oscillations with an amplitude A, which will vary as a function of frequency omega. It is the amplitude at 0 frequency by 1 plus omega square tau square power half. So as the frequency increases, the amplitude will come down. This is called the Debye relaxation formula, and we verify this formula with a serial light bulb. So I send a constant DC current I0 through the bulb, and I superpose on the DC current an AC current of constant amplitude I and different frequencies. So the temperature of the bulb will then vary as T is a steady temperature due to I0 plus a temperature which fluctuates at the frequency omega due to the AC current of amplitude I. I take I0 to be 200 to 300 milliamperes and the RMS value of the AC current to be 20 milliamperes. That means the AC current is only 10% of the DC current. Then T1 by T0 will be a few percent. The intensity of the light emitted will have a large DC value or steady component superposed with a small fluctuating component varying with frequency omega. I have a photodiode which picks up both the steady component and the fluctuating component. This photodiode has a relaxation time of the order of nanoseconds, whereas the serial bulb has a relaxation time of the order of milliseconds, tens of milliseconds. So the photodiode will react instantaneously, whereas the serial bulb will react slowly and the output of the photodiode is measured as a function of frequency from 20 Hz to 100 Hz. The output will decay according to the Debye formula, where tau is the slow relaxation time of the serial bulb, not the fast time of the photodiode. So in this box, I have a bulb, and this bulb, I send a current through this bulb by a stabilized 5-volt DC supply, and the current goes through 6 ohms and 2 ohms and the bulb. I have a switch, this switch here is shorted, so you get a maximum current, DC current flowing through the bulb. To know what is the DC current, I measure the voltage across 6 ohms. This voltage comes to this switch at the bottom. When I put this switch down, it will measure the voltage across 6 ohms, and this voltage is measured by connecting a DMM to the 2 banana terminals here. You can see that the voltage is 1.834 volts across 6 ohms. That means the DC current is 306 milliamperes. Now I connect a signal generator. I keep the frequency of the signal generator at 19.95, that is 20 Hz. I connect the signal generator to these 2 terminals. I keep the frequency at 20 Hz. This signal generator will send a current through the 1000 microfarad, the bulb, 2 ohms, 1000 microfarad, 50 ohms back. The 2000 microfarad capacitors prevent the DC voltage from coming to the signal generator. To know the RMS AC current, I measure the RMS AC voltage across 50 ohms, which comes to the same switch here. I put this switch up and I change the setting of the DC of the multimeter to AC. Then I get the RMS AC voltage across 50 ohms. I adjust the amplitude to keep this voltage 1 volt. So the AC RMS current is 1 volt by 50 ohms, that is 20 milliamperes. The photodiode gives an output 5.29 volts due to DC current. It will also give an AC output, which I can get by putting it in AC, and that is 187 millivolts, when the frequency is 20 Hz and the voltage across 50 ohms is 1 volt. I note this value and this frequency. I will now change the frequency to some other value. Let us say 40 Hertz. okay, 40 hertz. I keep the AC voltage 1 volt. Okay, and now I get an output of 92 millivolts, which is roughly half the value, 187 millivolts, we got at 20 hertz. This is because tau for the bulb is of the order of 100 milliseconds. So at 20 hertz, omega tau is 2 pi 6 into 20, 120 into 0.1. Omega 12 tau is 12. Omega square tau square is 144. It is large compared to 1. You can neglect 1 and then the denominator will become omega tau. That means the amplitude will decrease as 1 by f, 1 by the frequency. And that is what you see, the amplitude at 40 hertz is half the amplitude at 20 hertz. So what we do is, we change the frequency from 20 to 22, 24, 26, like that, always keeping the AC voltage across 50 ohms 1 volt. And then we take this photodiode output on this multimeter, AC output, I write it here. This is a different bulb and therefore the readings are different. I take the readings as I increase the frequency and I take the readings as I decrease the frequency. I take the average value of the readings. I take the reciprocal of these values here. I will repeat what I said. When the switch SW2 is put up, it shorts the 2 ohms and the DC current I0 through the bulb is a maximum. The voltage across 6 ohms comes to the DP/DT switch here, and when I press it down, the voltage across 6 ohms DC voltage comes to these 2 terminals, and that is measured across this multimeter, 2 3 decimal places. The bulb glows steadily due to DC current. So the light from the bulb is picked up by the photodiode, which will give a DC output. You can adjust the distance of the photodiode from the bulb by turning the screw. If you move the photodiode away, then the voltage will come down. If you move the photodiode away, this voltage will come down. Adjust this distance so that this voltage, DC voltage, is about 5 volts and lock it with the locking nuts. Now I connect a signal generator to these 2 terminals. The frequency is adjusted to 20 hertz. This sends a current through the bulb, and to know what is the AC current, I measure AC voltage across 50 ohms, which comes to the switch which I put up, and I change this to AC. You see that the voltage across 50 ohms is 0.997 volts. I must adjust the amplitude so that it is 1. Due to this AC current, the light emitted by the photodiode fluctuates, and therefore the photodiode will give an AC voltage. The RMS value is measured on this multimeter put in AC. It is 188 multimeters. Then I change the frequency to these values. At each frequency I check that the voltage across 50 ohms is 1 volt, otherwise I adjust the amplitude knob and I take the AC voltage of the photodiode, I take it in this multimeter while the frequency is increasing and while it is decreasing. This is the average value. This is 1 by average value, and I plot 1 by average value against the frequency. I will get a straight line. The average value of the frequency will vary as the average value of the voltage at frequency f will vary as V average at frequency 0 by 2 pi f tau, because omega tau square is very much greater than 1. So 1 by V will be proportional to f, and that is what you see here. The slope alpha is 2 pi tau by V average 0. So the AC part is over. Now I have to find tau. To find tau, I have to find V average 0, the AC output of the photodiode when the frequency of the AC current becomes very low. To determine this, we do a second DC experiment. I switch off the signal generator, I put this switch down and I put this switch down. When I put this switch down, then the 2 ohms resistor comes in parallel with this resistance in this box, which I have connected to these 2 terminals. Therefore, I can change the resistance in the DC circuit by pulling out plugs from the resistance box. This will change the DC current through the bulb in small steps. The DC current is measured on this multimeter when I put it in DC, and I measure the DC output of the photodiode. So you will see the current, DC current through 6 ohms produces this voltage 1.779. Correspondingly, photodiode output is 4.04 volts. Now I will pull out 0.2 ohms from here. So the current, the voltage across 6 ohms has come down to 1.766. It has decreased slightly. The photodiode voltage has come to 3.81. I pull another 0.2 ohms. So you will find I can change the current and measure the DC output of the photodiode. So the voltage across 6 ohms is changed by pulling plugs out of the resistance box, and it changes from 1.843 to 1.696 in the experiment which I did and which is reported here. So you divide this by 6, that gives you the current through the bulb, DC current. So you see DC current changes by a very small amount, not 2 amperes. This is the square of the DC current, and this is the output of the photodiode. We assume all the heat generated by the current in the bulb is converted to light, and the photodiode measures the intensity. In that case, I square must be proportional to the photodiode output, and therefore we plot a graph of the photodiode output against square of the current. This is an approximation. I fit a straight line through the points. The fit is not bad because the deviation of the point from the straight line is small. I calculate what is the equation for this line. The photodiode voltage is minus 13.96 plus 174.1 into I square. In my AC experiment, the voltage across 6 ohms was 1.862 volts, and therefore the DC current was 310 amperes. The RMS AC current was always kept as 0.2 amperes, 20 milliamperes. If RMS is 20, the peak AC current will be RMS into root of 2, that is 28 milliamperes. So this AC current is superposed on the DC. Therefore, the maximum current through the bulb is the DC plus peak AC, that is 0.338 amperes. As the frequency tends to 0, this would produce a maximum output voltage, V maximum, calculated from this equation by substituting I maximum here. And that voltage is 6.83 volts. The minimum current through the bulb is 0.310 minus 0.28 or 0.282 amperes. Substitute the square of the current in the equation for the straight line, that will produce a photodiode output of 0.28 volts. So as f tends to 0, photodiode output will alternate between V maximum and V minimum. So the peak AC variation in the photodiode output voltage is V maximum minus V minimum by 2, and this value is the peak value. The RMS value is obtained by dividing the peak by root 2. So the RMS value is 6.83 minus 0.28 by 2 root 2, that is 2.14 volts. This is the V0 here. This is the V0 here. So you know the slope, you know V0, you calculate tau. So tau is alpha V0 by 2 pi, that comes out to be 0.15 seconds or 150 milliseconds. I now use the Debye equation with V0 and tau, which I have found, to calculate what the output voltages would be according to the Debye equation at all these frequencies. I plot the calculated value against frequency as this continuous curve, and the experimentally measured values are the points. You see that the agreement between the measured value and fit to dBy formula is very good, and therefore we verify the dBy relaxation formula for the serial light bulb.